Let's have a look at this awesome question on work energy theorem. The force displacement graph of a particle is shown below. Yes, we can see how the force is changing with displacement. If the particle has mass 2 kg and has initial velocity of 2 meter per second, mass is given and the initial velocity is also given. Calculate final kinetic energy of the particle when it displaces from x is equals to 1 meter to x is equals to 5 meter. So, the particle is displaced from 1 to 5 meter. And when the particle is at 5 meter, we have to tell what is the kinetic energy of this particle. What is this final kinetic energy? This is the question. Now, we are asked the kinetic energy. And what are we given? We are given the force versus displacement curve. Well, what is the trick? What is this mystery? Well, here is work energy theorem. Work energy theorem says work done by all the forces is equals to change in kinetic energy. And we can arrive at the final kinetic energy if we calculate the work done by all the forces on this object. Yes. And how can we calculate the work done? Well, using this force versus displacement curve, we can find the area under the curve. And that would give us the work done on this object. Okay, we got this way. What we will do is we will say the change in kinetic energy is kinetic energy final minus kinetic energy initial. And this would be equal to the work done on this object. Work done is F dot ds integration. And this integration of F ds is actually the area under force versus displacement curve. We just have to find out the area and this will give us this integration, and from this we will calculate what is the final kinetic energy. We got our way clear. So let's not waste our time and let's quickly calculate what is the area under this curve. Now the parts which are above x-axis will be considered as positive and the parts which are below x-axis will be considered as negative. Yes. So what about this part? This is the first part. This part has the base as 1. 2 minus 1 is 1 and the height is 10. So the area of this rectangle is simply 10. Good. 1 times 10 is 10. Now let's consider the second part. The second part has the base as 3 minus 2 which is 1 and the height of this part is 20. What is the area? Area is 20 times 1 which is 20. Good. Now the third part. The third part is interesting. What do you think about the area? Will we take the positive area or the negative area? Come on. Will it be positive or negative? Yes, it is negative. Why? Because it is below x-axis. So, what is the base? 4 minus 3 is 1. This is the base and the height is of length 20. But the area will be negative. It is minus 20. Oh, we got that. Now comes the fourth part, and this part is actually above the x-axis, and we can see that this part is having the base as 5 minus 4 which is 1 and the height is 10. So the area is 10 times 1 which is 10. Great. This gives us the total work done on this particle up to 5 meters. And we can see that the total work done is just 20 joules. This is the total work done on the particle. So this integration is 20. Now tell me the value of initial kinetic energy and I will tell you what is the final kinetic energy. Because final kinetic energy final is equal to 20 plus initial kinetic energy. And we know the initial kinetic energy will be half into m into v square. Now what was the mass of the object? We know mass of this object is 2 kg. Okay, and the initial speed is 2 meter per second. So let's just put the mass to be 2 kg. Now let me just talk about the initial speed. Let's say when the particle was at zero displacement, its speed was 2 meter per second. 2 meter per second. Now this speed won't change if there is no acceleration, right? Right. Now we can see between 0 and 1, what is the net force on the object? There is no force on the object. So we can say there is no acceleration. What is the speed at 1 meters? What is the speed at the displacement 1 meter? You will say speed will remain same. It will be 2 meter per second. Yes. And after 1 meter the speed will change because there is some force and acceleration. So at 1 meter the speed is 2 meter per second. So the initial speed we will write as 2. Great. And we can see that this calculation is giving us the value of 24 joules. This is the final kinetic energy of this object, and we can mark option A as the right answer for our question. Let's look at this awesome question on rain. Consider a raindrop of rainwater. Well, raindrops are of rainwater, isn't it? Having a mass of 1 gram falling from a height of 2 kilometers. So it is covering a distance of 2 kilometers from cloud to the ground. It hits the ground with the speed of 50 meter per second. Okay? The work done by the resistive force of air is. So, what all is given? It is given that the raindrops hits the ground with the final speed of 50 meter per second. This is the final speed of raindrop. In the downward direction, we have the velocity, and we can see that there is some displacement of the raindrop. And the displacement is actually in the downward direction. It is 2 kilometer. And raindrop finally hits the ground. During this entire process, we have to tell what is the total work done by the resistive forces on the drop. What is the work done by the air resistance? This is the question. Now, we know there is some change in kinetic energy. Definitely, the raindrop starts with zero kinetic energy and finally it gains kinetic energy. There is some change in kinetic energy. And work done is asked in the question. So, do we have any formula which relates work done and change in kinetic energy? Yes, we do have a formula. That is from work energy theorem. Okay, tell me the formula. The formula is work done by all the forces is equals to change in kinetic energy. Very good. Now, what all forces are doing work on this drop? Well, we can see two forces on the drop. One is force due to gravity in the downward direction, and one is force due to air resistance, and that is in upward direction. Fine. Only these two forces can do any work on this drop. Great. So, work done due to gravitational force plus work done due to this resistive forces, this will be the total work done on the drop, and that would be equal to change in kinetic energy. The final kinetic energy will be half m. Mass was 1 gram, so we can write it 1 upon 1000 kg, half mv square. Final velocity is 50, so 50 square minus initial kinetic energy. Now, what is the initial kinetic energy of this drop? It leaves the cloud with zero initial velocity. So, what is the initial kinetic energy? Yes, it is 0. Okay. Now, if we calculate the work done due to gravitational force, we will find the work done due to resistive forces. Okay. So, tell me the work done due to gravitational force. You will say, well, that would be equal to force, the gravitational force times the displacement of the object. And let me tell you, both the gravitational force and the displacement of the object, both are in downward direction. Let me again draw the cloud. Here is our cloud, and we can see the displacement is in downward direction, and the gravitational force is also in downward direction. So the dot product will come out to be positive. Okay, so we can write the magnitude of gravitational force. It is mg, and m is 1 upon 1000. This is 1 gram, and 1 upon 1000 kg. M into g. G is 10, and the displacement has the total value of 2 kilometer or 2000 meters. We can see 3 zeros cancels out straight away, and work done due to gravitational force is 20 joule. Gravity will do a positive work. Okay, so let's write the work done due to resistive forces like this. We have the final kinetic energy. It is coming out to be 1.25 joules, and if we take the gravitational force on the other side, we will get negative. This is minus 20, and work done due to resistive forces is coming out to be minus 18.75 joules. And do you see minus over here? Yes, we see minus. What does this minus indicates? Well, it indicates negative work. This means air is actually taking energy out of the raindrop. Yes, you are right. And we can also verify that the resistive force is in upward direction and the displacement is in downward direction. So when we take the dot product, we will get something negative. Both the vectors are 180 degree apart. So we will get negative work done. And we can mark option C, 18.75 joules minus 18.75 joules as the correct answer for our question. A bomb is dropped on the enemy post by an aeroplane flying horizontally with the velocity of 60 kilometers per hour at a height of 490 meters. It was flying really high, 490 meters. And its velocity, I don't know what is going on, and it is flying with 60 kilometers per hour. Even my bicycle goes faster than this. At the time of dropping of the bomb, how far the point on the ground directly below the aeroplane should be from the enemy post so that the bomb may hit the target? Now, before I tell you what the question is asking us, let me replace this aeroplane by my helicopter. These days, I usually don't prefer aeroplanes, Now, at the time of dropping of the bomb, there was a point just below the helicopter. Let's say this is point P. We have to tell what is the distance of this point from the enemy post. This value, the horizontal displacement x0, is asked in the question. Now, can you guess the path of the bomb? Can you guess the trajectory? You will say, yes, we can guess the trajectory. Okay, so what would the trajectory look like? You will say, well, we see a projectile motion over here, and the trajectory is like this. Yes, and here goes the bomb and hits the target. Now, you might have noticed that the bomb, when it was inside the helicopter, was moving along with the helicopter. Yes. So when we just release the bomb, the horizontal component of the velocity of the bomb is actually equal to 60 kilometers per hour. The velocity of the helicopter itself. Okay, we got it. So, as the bomb is dropped, its initial velocity is 60 km per hour in the horizontal direction, and it further gains some velocity in the vertical direction. It has horizontal displacement as well as vertical displacement, and finally it hits the target. We have to find what is the total horizontal displacement of the bomb when it was released from the helicopter. This is the question. Now, let us see that this point at which we release the bomb is the origin. From this point, we can find the coordinates of the bomb as a function of time. Let's say at time t, the coordinates are x, y. The x component, this is the easiest one to find out. X component is ux, the horizontal component of the velocity of the bomb, times t. The horizontal component of the velocity does not change with time because there is no acceleration in the horizontal direction, right? Right. Now, can we tell the y component? Yes, we can tell the y component. Y component actually depends on time. Y is equals to minus half gt square, because in the vertical direction there was no initial component of the velocity. Yes, so uy was 0, hence we can write y is equals to minus half gt square. Yes, we can write that. Now we can place the value of time from equation 1 into equation 2, or place the value of time from equation 2 into equation 1, and we will get the equation of the trajectory. Right? And we have to find the value of x naught. So at the instant y is equals to 490 meter, we can find the value of x naught. Yes, we can find the value. So let's proceed. Now y is equals to minus 490. This is the vertical displacement. I write negative because y is in the negative direction. It is below the origin. And this is minus half gt square. Now g can be written as 9.8, and 9.8 divided by 2 will be 4.9. That would be useful. And we have t square over here. Let me just write t naught square. Now from this we get the value of t naught. It is 10 second. 10 second. Okay. Now at the time t is equals to 10 second, can you tell me what is x naught? You will say yes. It is ux times t naught, and t naught is 10 seconds. Good. Now this ux, what is this ux? Ux is 60 kilometers per hour, but this is in kilometers per hour, and we have put the time in seconds. So why not convert 60 kilometers per hour into meter per second? This would be 60 times 5 by 18. This is how easily we convert kilometers per hour into meter per second. And this is giving us 500 by 3 meters. This is the value of x naught, and this is the answer for our question. So we have solved the problem completely. And I don't know why these two guys are still in the tent. Isn't it time to go out of the tent? Well, bye-bye guys. Woo! They were superheroes all along. I didn't even knew that. Well, let's mark option B, 500 by 3 meter, as the correct answer for our question. The kinetic energy k of the particle moving along a circle of radius r depends on the distance covered, as k is equals to alpha s square, where alpha is constant. So a particle is moving in a circle, and the kinetic energy of that particle is dependent on the distance covered by the particle. K is equals to alpha s square. This is given in the question, where alpha is a constant. Alpha is a constant. The force acting on the particle is. Now we have to tell what is the net force on the particle. Again, what is given? Particle moving in a circle. Radius of the circle is given, and the kinetic energy of the particle, half mv square, is dependent on the distance covered. It is equal to alpha s square. Alpha is a constant, by the way. And what is asked in the question? The net force on the particle is asked. What is the net force acting on the particle? You will say, well, if we know the net acceleration of the particle, we will get the net force. Yes. So net force is mass times net acceleration of the particle. Well, great. Now, how do we get the acceleration of the particle? Well, we can see the particle is moving in a circle. So it must have some centripetal acceleration, isn't it? So there is some centripetal acceleration. We will call it AC. Now, is there any tangential acceleration of the particle? You will say, well, the speed is varying with distance. So as the speed is changing, there is some tangential acceleration, right? So tangential acceleration is also there. We will call it AT. And you know what? The resultant of these two, the resultant of AC and AT, will give us the total acceleration of the particle. This is acceleration A. And from this acceleration, we will calculate the required force on the particle. That's how we solve this problem. Now, the thing is, we must know what is AC. So how do we calculate AC? Well, there was a famous formula. The centripetal acceleration is equals to v square by r, isn't it? Now, what is the value of v square? Well, we can have the value of v square from this equation. V square is equals to 2 alpha s square by m. Okay. So let's divide both the sides by r. So we have the value v square by r, and this is giving us centripetal acceleration. Hooray! So we got the centripetal acceleration. Fine. Now let's talk about the tangential acceleration. Well, tangential acceleration. By the way, what is this tangential acceleration? What was the definition of tangential acceleration? You will say, well, if we try to define tangential acceleration, we must know how the speed is changing. In fact, the definition of tangential acceleration is rate of change of speed. So this is dv by dt. But we know how the speed is changing with distance covered. Okay, no problem. We can have some other formula also. We can write this like v dv by ds. Oh, now we can find AT. Great. So let's go on a mission of finding AT. Now let's differentiate this equation, which is half mv square is equals to alpha s square. Both the side let's differentiate with respect to distance covered. Okay. And then from this we will find out what is the value of tangential acceleration. Okay, let's do it quickly. Now, when we differentiate the left side, we get m by 2 out of the differentiation. And when we differentiate v square, just v square, we get 2v dv by ds. Okay. And on the other side, we have alpha as constant. And when we differentiate s square, we get 2s. Oh, very nice. Now we know what is the value of AT. So let's substitute the value of v dv by ds as AT. And from this we are getting AT as 2 alpha s divided by m. Okay, we got what is AT now. 2 alpha s by m. And we also know what is AC. AC is 2 alpha s by m times s by r. So we got AT, we got AC. Now what do we want? We want the total acceleration, isn't it? Now how to get the total acceleration? Well, total acceleration A is equals to whole under root of AC square plus AT square. Yes. And we know 2 alpha s by m. This will come out as common. And then we have the total acceleration as 2 alpha s by m as common times whole under root of s square by r square plus 1. Okay, we got the total acceleration now. But do we know what is the net force on the particle? Yes. Let's multiply both sides by m. So we have ma as total force on the particle, and this is 2 alpha s whole under root of s square divided by r square plus 1. Well, now after all this calculation, we finally got what is the force acting on the particle. We can now mark proudly option B as the right answer for this question. A variable force acts on a particle of 1 kg such that the acceleration as a function of time is given by A is equals to 2t. So we know how the acceleration is varying with time. Acceleration is not constant, it is varying with time. And we know the function. Okay. The particle is starting from rest. So we know the initial speed of the particle u is equals to 0. Great. Find the work done by the force on the particle in first 3 seconds. So what is the work done on this particle in first 3 seconds? This is the question. We have to find the work done. Now, do you remember the work energy theorem? Yes, we do. What is the work energy theorem? Work done by all the forces is equals to change in kinetic energy. Well done, well done. Now, change in kinetic energy is nothing but the final kinetic energy minus the initial kinetic energy. Okay. To get kinetic energy, we must know what is the velocity of the particle, isn't it? Yes. How to get the velocity of the particle? We know acceleration as a function of time. Can you tell me the velocity of the particle as a function of time? Yes, we can. Okay, tell me. Well, you will say, instead of acceleration, you can write rate of change of velocity, dv by dt. Well, we can write that. Now, this gives us a differential equation. Can we solve the differential equation? Yes. We can write this differential equation in a different style. Let's take all the terms containing time on one single side. So we have 2t dt over here. And this is equal to dv. Now let's integrate both the sides. So when we put the limits of the integration in time, we will put t is equals to 0 to t is equals to 3. Now, let's put the limits of the velocity. What is the velocity at time t is equals to 0? Again, what is the velocity at time t is equals to 0? You say the particle starts from rest. So, the initial velocity is 0. Okay. And let the velocity at time t be v. So, we have v over here. Now, when we perform this integration, we get v is equals to 2 t square by 2, and we put the limits 0 to 3. So we are getting 3 square minus 0 square. This is simply 9. So the velocity at 3 seconds is 9 meter per second. Okay, we got the final velocity. Now, let's find the change in kinetic energy, and that would be the work done, and work done was asked in the question. So, what is the final kinetic energy? Well, it is half m v square. V final square is 9 square. And what is the initial kinetic energy? Initial kinetic energy is 0. Why? Because the initial velocity was 0. Okay. So, initial kinetic energy is 0. Now, 9 square is 81, and 81 divided by 2 is 40.5. Yes. So, the work done on the particle is 40.5. And we can mark option B as the correct answer for our question.